One final note about storage, particularly when it comes to hard drives. Hard drives have a fixed speed. Looking at the inside of a hard disk, we can see a large platter that spins around. The speed at which we can read from the hard disk is largely determined by how fast the platter spins. It also depends a great deal on where the data is located. We can see the outside of the platter is actually moving faster than the inside, so storage on the outside will be retrieved more quickly. Nonetheless, there is still a finite speed. This speed is generally measured in IOPS, or input-output operations per second. Typically, hard disks might get around 90 to 100 IOPS. An SSD, which uses technology similar to an SD card, doesn't use a platter. SSDs, or solid-state drives, can sometimes reach up to 100,000 IOPS. In either case, for large businesses running massive databases, even 100,000 IOPS may not be enough. So what do businesses do? Businesses requiring high speed on storage utilize RAID. RAID stands for Redundant Array of Independent Disks. It's simply a way of stringing multiple hard disks together in order to increase IOPS and redundancy. There are multiple configurations known as RAID levels. Here is how a few of them work. RAID 0, known as striping, is a way of maximizing the speed of disks. Consider the following setup. Each disk can handle 100 IOPS. Now we put two of them together, and the computer, if it has to write, writes half to each disk. This means it can write twice as much data in a given amount of time than it could with a single disk, giving us 200 IOPS. Continue adding these disks, and we can continue to increase IOPS in a linear fashion. There is a problem with this setup, however. I'm sure a number of you watching this video have had a hard disk fail. The reality is hard disks can and do fail, and the larger the amount of disks you have, the more odds you have of getting one of these disks that will fail. In a RAID 0 setup, if any disk in the set fails, the entire data is gone, since it is missing part of the set required to complete the data. The next RAID level is RAID 1. RAID 1 is known as mirroring. In this type of RAID, every time data is written to one drive, it is simultaneously written to another. In the case of mirroring, there is no increase in speed, but there is added redundancy. If one of these drives were to fail, we would still have a complete copy of the data. Thus, the system could continue operating without any outage. While RAID 1 works well for redundancy, it doesn't help with speed. Further, it increases costs. Now, regardless of the amount of data we use, we will have to purchase twice as much storage for it. This is where the next RAID level, RAID 5, can help. RAID 5, known as striping with parity, is similar to RAID 0, but allows for parity. Let's take a simplified look at how this works. Each disk in the array stores data as, yep, you guessed it, ones and zeros. If we zoom in really closely, we might see something like this. Now, RAID 5 is made up of multiple disks, and if we stripe this direction, we can count the number of ones in each position. When writing to the drive, one section on each are set up for parity, making it either a 1 or a 0, so that the number ones on each position will always be even. Now, if there is a failure of a drive, the system can extrapolate the missing data based on the knowledge that there must be an even number of ones in each position. IT can replace the failed drive and the system can rebuild it again. This version of RAID has the advantage of the striping of RAID 0, but allows us some redundancy, making it cheaper than RAID 1.